Okay, Assalamualaikum warahmatullahi taala wabarakatuh. Okay, today we will continue with the Kolmogorov-Sinai theorem in lecture 12 on Tuesday. Okay, so let us recall the Kolmogorov-Sinai theorem. So let this triple be the measure space. And T is the measure preserving transformation. So for any A in F, we have that the measure of the pre-image of A is equals to measure of A. This is for the measure preserving transformation. So for the Kolmogorov-Sinai theorem, this theorem is actually the theorem to find the entropy of the transformation. Okay, so in order to find the entropy of the transformation, we need two properties. So the first one is for any the finite partition psi, okay, we must have the entropy definition as the following sum. That is, entropy of the partition psi is equals to the summation of I from 1 to n mu of ai multiplied with the log mu of ai. So this is the first property. And we know that the entropy is non-negative. Okay, next. So if we have two partitions and this partition psi is less than or equal to eta, so here eta is the another partition that has m element. Okay, so that means we have our entropy of the partition must be less than entropy of the second partition eta. Okay, so we have covered the first property here in the previous lectures. So we also know how to find the entropy of this partition. Okay, for the second property, we have the entropy of the transformation related to the respect to partition psi, or we can have we call it as a relative entropy of measure preserving transformation relative to finite partition. Okay, so we know already, and we have the definition of this relative entropy is given by this limit 1 over k multiplied with the entropy of the joint of the pre-image of the elements in the psi. So the limit exists. If the limit exists, it can be either finite or infinite. Okay, so we're having these two properties. Only then we have the Kolmogorov-Sinai theorem. So Kolmogorov-Sinai theorem is given by this definition. So we have the entropy of the transformation is given by this definition, which is the supremum of psi of the entropy of the relative to partition. So we call it as supremum of the set. Okay. So actually, generally, Kolmogorov-Sinai theorem is to find the entropy of the transformation here. This one. So in order to find the entropy of this transformation, you should know the entropy of the partition and the entropy of the transformation related to partition. Only then you can have the entropy of the whole transformation. Okay, you can have a home task for this case. You can do this on your own. Okay, home task. Okay, let X be finite. Okay, try to find the entropy. So X is given by this element A, B, C, D. And on Tuesday, we have discussed about the smallest and largest set, right? So you have the smallest set is the whole X. Okay, the largest set you should define something. So the largest set should be what? A, because epsilon is the set that has a single element. B, C, and D. This is the largest. So in between the largest, in between the smallest and the largest set, you have several other set, which is, okay, I can define as partition 1 as A, B, C, and D. Okay, and then I can define partition 2 as A, B, D, and C, and so on. So I think you know, you can list all the possible elements in the partitions. Is that okay? You can go for 3, B, C, D, and A, and so on. So you can consider 3 and 1 element, 3 element in a set, 1 element in a set, and you can consider 2 element in a set and another 2 element in a set, and so on. Boleh this part? Okay, so let's say you have all the lists. I think in the previous example of major preserving transformation, I think you got 13 partitions, I think. 13 partition. Okay, you can check. Okay, now we let T be the ergodic transformation. So for ergodic transformation, what do you have? So if you have A, B, C, D, one of the examples, we can have A to B, B to C, C to D, and D to A. So how can you differentiate, determine this transformation is ergodic? Remember, one of the properties that you can see is they are cycle. So cycle maksudnya A to B, and then from B to C, and then from C to D, and then from D to A. Dia macam cycle A, B, C, D, and then to A. So if the transformation is in a cycle form, then you can say that the transformation is ergodic. Okay, so in this case, what is the measure for this transformation? So I can have V of A equals to V of B equals to V of C if equals to V of D, which is mu lah, mu. This is 1/4 because I have 4 elements. Okay, your question is find, this is the question, find relative entropy for each partition. Each partition, 13 partitions altogether. So I have, so first you can find T and psi 1, T and psi 2, and until T and TV and T epsilon. So this is the smallest, this is the largest. Okay. So maksudnya 13 partitions you have here, including the V and also the trivial partition and also the largest partition, which is epsilon. Okay. Any questions until this part? Okay. The answer should be 0. The whole, all of them. Because you can take the largest for the supremum, right? And later on, you can check that this is 0. Because previously, we also showed that the relative is 0. Okay. All right. If no questions, then we go to the next definition. Generator. For measure preserving transformation T, a finite partition psi is called generator if you have the join, okay, join partition, pre-image of the partition of the psi is equals to the largest partition. So that means largest partition. So if you have a measure preserving transformation T and you have a finite partition psi, so the join of the infinitely many pre-image of the partitions is equals to the largest partition. So if you have they are equal, that means your T or your measure preserving transformation T is a generator. For example, I consider again this segment 0 and 1. And I consider the dyadic transformation T. 2x is mod 1. And then I have the partition psi. Again, I like to have the symmetric partition. And okay. So if you define in the dyadic punya transformation, how can you write your x? The x. So can be written as 0.x1, x2, x3, and so on, right? Okay. So for this case, since we have two elements in the partition, so I can have the x0 lah. x1. Okay, here in this first digit, x1 is 0. Here in the first digit, x1 is 1. There, x1 here. Right? Okay. All right. So now we want to show that the left hand side is equal to the right hand side using this. So what do? Next, you have to find the pre-image. The join. the join of psi and the pre-image of psi. So what do you have here? So you will get psi joined with the pre-image of psi is equals to, so taking the the pre-image of the first, take this one first, okay? Pre-image of this one first, what do you have? So actually kita macam divide lagi dua. 0.5 punya segment kita divide lagi dua. Okay, so you will get 0 and 1 over 4. Another one, 1 over 4 to 2 over 4. So for this case, you will get x1 0, x1 0, x2 is 0 for this position. This one x1 is 0, x2 is 1. Okay, now if you write more for this one, you can have 2 over 4 to 3 over 4 until 3 over 4 to 1. Okay, so in this case, what you mean is so x1 here is 1, x2 here is 0. Here x1 is 1, x2 is 1. Macam kita divide, if you remember the mechanism. So first we have 0 and 1. Okay, and then you divide, you take the pre-image between this. In the adik, what do you have? So it's like you dividing again these two into 2. So here you have 0, 1. And 0, 1. And then this part here is 0, this part here is 1. So this is what happened. Okay, and again and again. So if you go for now for this is for the join of the pre-image of the partition. So this is only the first pre-image. Okay, now you can find for the join of the 3 pre-image or three partitions. So what do you have? I have psi join with the t minus 1 psi join with the t minus 2 psi. Okay, so for this case, it's like you fixing. You repeat with the previous punya methodology, and I can write in general form. So x1 is equals to I1, x2 is equals to I2, x3 is equals to I3, where this I1, I2, I3 is equals to 0 or 1. In general form, I can write in this way. Okay, apa maksud dia? Sebab tadi kan kita akan previously we got x1 equals to 0, x2 equals to 0, x1 equals to 0, x2 equals to 1, and so on. So this is all the dia punya digits that it can be for the case of joint 2 partitions. So if we have 3 partitions, that means you will have 3. x1 equals to 0, x2 equals to 0, x3 equals to 0. And this I, which is 1, 2, 3 subscript dia ni, can run from, it can be until 0 or 1 saja. So you will have berapa many possibilities, for example. You have 8, right? Sebab 2 kosong 3. Sebenarnya, you kalau nak list down, you will have 8. So in general, you can write, so if you go by induction, okay, you can have, if you have infinitely many, finitely many joint partitions, finite So I have berapa? Until how many x you can have. So I have x1, I1, x2, I2 until xk, ik. Okay, it's like you fixing all these coordinates. So kalau k to goes to infinity, what happens? That means we are fixing all the digits. We are fixing k plus 1 punya digit equals to ik plus 1, k plus 2 equals to ik plus 2 and so on. So sampai infinity. So if you fixing all the digits, what happens to the number of the elements in the sequence of this set? If k equals to infinity, then that means we have only a single digit saja with infinite sequence. What does it mean by this? It means that our numbers of element is equals to the numbers of the largest element, which is the epsilon. Faham tak? Is that clear, this part? Okay, let me repeat. Boleh? Okay, jap. Okay, kita repeat sikit, saya ulang. Okay, first, the definition of generator. So, kalau we have a measure preserving transformation T, it can be anything. Bernoulli boleh, diadik boleh, triadik boleh, Bakers pun boleh. So, and we have a finite partition called generator. So, this finite partition is called generator if we have the join of the infinitely many T of the partition is equals to the largest partition. Okay, first I consider the segment 01 with dyadic transformation. So dyadic transformation can be defined by this way, right? X equals to 0.x1, x2, x3 and so on. So first I have the partition. So partition I have 0 to half and half to 2 because half to 1 because we have I have 2x. So that means I have only 2 elements in the partition. 0 sampai 1 je. So kalau psi in these two partitions, the first digit always 0 because from 0 to half, this is 0. The second digit which is x1, ni x1, maksudnya x1 ni adalah apa value dekat sini. Okay. Kalau 0, kalau x1 is 0, that means the element is between 0 to half. Kalau x1 ni adalah 1, the element adalah between half to 1. Okay, right. So I join this partition. So I take the pre-image of the partition. Okay, so the pre-image between 0 and half. So that means we actually and half and 1. We actually taking the pre-image of dia sebenarnya kita divide lah. Dia macam contoh kita divide. Kalau 0 dengan half kita divide lagi 2. So we have another two elements. So I have 0 to 1/4, 1/4 to 2/4 and so on sampai 1. So for this case, kalau kita divide 0 to half into another 2, so I have the first digit x1 here is 0, x1 here is 1. Salah, x2. So ni x1, so di sini x2, x1, x2. So kalau kita divide 3, that means x1, x2, x3. in 0 and half punya apa tu segment. Again the same for this case between half and 1. So between half and 1, the pre-image of that is between you got this. So between half and 1 is the 1, right? So x1 is 1, and if you divide lagi by 2, so I got x1 is 0, x1 is 1 sebab dia 1 kat sini, and then x2 is 0, or x1 is 1, x2 is 1. Okay, until here okay tak?
Okay.
Alright. So if we go to let's say I try to do for this case kan. This one. For this case, let's say I write in terms of macam previous example. So I have x1 is what? So that means I divide 0, 1. So I divide 3 times. So half. And then this is 0 and 1. For this case, I have divide lagi. So I have 1 over 4, 1 over 2, and 0. Divide this another 2 kan. Okay, so I have here 1 0, 1 over 8. You will have until 1 over 8 lah. Sampailah kat sini 1 over 2. 4 over 8. 4 over 8. So 0, 1 over 8, 2 over 8, 3 over 8. Okay, so if you got this, oops, okay, here 0, again this 1, here 0, 1, and then 0, 1. So for the case of this one, x1 is 0, x2 is 0, x3 is 0 for this one, 0, 0, 0. So for another case, x1 is 0, x2 is what? 1 here, and x3 is 1. 0, sorry. So dia kena consider all. 1. x3 is 0. And then you consider 0. So you will have 3. x1 is 0, x2 is 1, x3 is 1. So this is what happens. So for this is for, sebab tu dia ada 1, 2 dengan 3. Okay. So this I1 can be 0 or 1. So kalau x1 can be 0, dah ada 0. And then ada x1. And then you can go further. x1 equals to 1 pula. For this case. And then x1 equals to 2 pula. 0 or 1 saja. So you will have how many possibilities here? Banyak kan? So dia baru 3, so you can find another. This one you got 4 ni, maksudnya ni lah dia punya. You fixing the coordinate between dalam ni. All of this is in one segment. So kalau you have one, this one you got 4. Dalam 4 segment you got these 2 coordinates. You fixing these 2 coordinates. So kalau dalam 3 partitions, so you will have 8 lah. 8 I think. You will have 8. So this is 1, this is 2, this is 3. So you have to find another. Okay, sampai cukup semua. And then you go, let's say, and then you do induction. Buat lagi join for t to the power of -3 psi. So you will get more and more elements in the joint partition, in the joint set. So what if you got k finite element, that means you will have finite jugalah kalau dia finite. But if k now becomes infinity, okay, ni if k is infinity, then you will have what? That means you are fixing all the coordinates to all digits, all. So how do you think berapa banyak? Maksudnya dia akan jadi single digit, betul tak? Sebab kalau kita fixing the first coordinate, 2 coordinate, 3 coordinate, 4 coordinate, 5 coordinate sampai infinity punya coordinate, dia jadi single digit. Bila dia single digit, maksudnya this is the largest digit. The largest elements that can have in the partition. Dia bukan number atau cardinality, dia merujuk kepada largest partition. Because we are fixing all the digits. And it has infinite sequence in the digit. Boleh tak? Masih tak faham? Ya?
Maksudnya dia bila dia ke infinity tu, dia akan pergi ke semua point ke macam mana?
Dia maksudnya dia punya coordinate sequence dia akan jadi 0 point. Dia fixing all. Dia fix. Okay, let's say lah x1. Okay, 0.x1 kan? Okay, so x1 can be 0 or 1. Betul? So you can fix x1 ni can be 0 or 1. So kalau x1 is 0, x2 is 1, let's say you fix the value of the x1, x2, x3, the sequence. Ni, x1, x2, x3 in this sequence. Kalau you fix this value, that means this is the largest. Kalau sampai sampai infinity, k. You can be 0.0111101110 until infinity. So this is the largest partition. So yang kita buat ni adalah possible values. Sebab x1 can be 0 or 1, so kita boleh list lah possible values dia. Walaupun possible values dia, tapi dia still finite, betul? Kita masih boleh kira. Boleh? Boleh? Ni, maksudnya I1 here can be 0 or 1, right? So you can fix any number. So 0 point 0, 0, 0, 0, 0, 0, 1 sampai berapa kali? The last one? 3 je. Okay, sebab ada 3 ni. Lepas tu you can have 0.101, then 0.001, 0.11 and so on. Betul? Tapi dia fix, betul tak? You have only 3 belakang je. 3 digit belakang. Last kali 0.111 lah. Boleh? So ni finite, you can count. Kalau buat sampai k pun, you can still count because this is finite. Betul? Until here boleh sampai ni.
Boleh.
Oops. Boleh Okay, so generator ni kalau dia sama, kalau join dia infinitely many and then dia sama dengan largest partition. Maksudnya you join many times. You join dia punya pre-image to many times. Maksudnya you divide infinitely many times. So your answer would be this lah. Dia hanya ada single digit sebab you fixing all. Okay, you fixing all. That is the largest partition. Senang kata bila kita join banyak-banyak kali, kita akan dapat sama dengan epsilon. Okay. So kalau you got this, that means this is you can conclude that your psi is the generator. So kalau you got the join of the pre-images infinitely many times is equals to the epsilon, which is the largest partition, that means you have the generator. Dia senang, dia ataupun kita selalu buat psi ni adalah finite, betul tak? Kita ambil psi ni finite. So if you join finitely many times k, and then you go for k square, you go for k cube, k something, you still until the join of the finite itu. Lepas tu k square boleh join lagi dengan k cube, k power 4 and so on, and then infinitely many times lah. And you got the largest partition. At the end, you still got the largest partition. Tu je maksud dia. So in this case, our psi is the generator. If you got the, if you can show it is equals to the epsilon. Okay, next. Another example. Let's try to check to do for triadic. So triadic Tx is 3x mod 1. Okay. So I have psi is given by this element. So A, because 3x, I divide into 3 partitions, 3 elements. 1/3 to 2/3 and 2/3 to 1. Okay. So in this partition, x1 here is 0, x2 here is 1, x1, semua x1. The first digit x1 is 2 because your x is boleh di write by this way. Okay. So this is the first digit. Okay, so kalau triadic, you can have also the same lah. Because if you show, kalau you do like you do for the diadic, you can get the same. That means you will have that your psi is the generator. Because you join the finitely many pre-images, finite partition, and then you divide again, so you can have that the last one would be the largest is equal to the largest partition. So in general case, so if you have Tx is equals to Rx mod 1, where R is between what? Anything. So I can have your psi to be 0, 0 element to 1/r, and then 1/r to 2/r until r minus 1/r until to 1. Okay. So, and then again, you have the first successive, you fix the first successive position, and then you fix the first and second successive coordinate, and then 1 second and the third successive position or coordinate, and until R, first, second, third until R position. So at the end you will get this is equals to the generator, is equal to the largest partition, which is, that means our psi is the generator. Our psi is the generator. Okay. Any more questions for this part? Okay. If not, then can we do the next example?
Yes.
Okay. Okay, no. Example number 3. Next example, I consider Bernoulli. So Bernoulli has this E set with the measure of P1 and the measure of 1 is P2. Okay, and you have the omega taken from this set. I have the partition function of EI, where EI is equals to E. So let T be the Bernoulli shift. So I have the partition to be a coordinate function x0 omega is equals to 0, and the second one at 0 omega is equals to 1. Okay, coordinate function. So the main idea is I want to fixing first coordinate, okay, 0 or 1. So that means x0 omega is equals to 0. That means you fixing the first coordinate, either you can be 0 or 1. And your omega is your cylinder set, a sequence, sorry, is given by this sequence. Okay, now I want to find the join of this partition. So kalau kita join psi and the pre-image of psi, that means you are combining, or you are finding the pre-images of the, so that means you fixing two coordinates. So I can have x omega equals to x1 omega equals to 0. So that means you're fixing two coordinates, 0 and 1. And last one you will have, so I can have another x0 omega is 0, x1 omega is 1. Next I have x0 omega is 1, x1 omega is 0, and last one I have x0 omega is 1, x0 omega is 1. So I have 4 elements. So that means in this case I fix two coordinates. Okay, and if you go for join of 3 partitions, so you will have 8 coordinates and so on. So lastly, in general, you can have the join of the finitely many pre-images of the partition. I have, so that means you are fixing kth coordinate. Okay, so I have x0 omega is equals to I0 until xk minus 1 omega equals to ik minus 1. Okay, and this give you the largest partition, right? You are fixing kth elements. So that means your coordinate ni maksudnya can be I0, can be 0 or 1. So you will have many elements in this joint partitions, and this would be the equals to the largest. So if k goes to infinity, then this is true lah. Then I have v k minus 1 equals to 1. Okay, right here proper way. So you for this case you are joining kth partitions, and by joining kth partition that means you are fixing kth coordinates. Okay. So in this kth coordinate you will have many elements dalam ni. And if k goes to infinity, then you will have that the whole joint partition until infinity here would be equals to the largest partition. Okay, this part. Questions? Ya.
Maknanya kalau dia sama dengan epsilon ni kan dia generator. So untuk dapatkan harga epsilon, kita kena buat k infinity kan, infinity. So maknanya dia generator ni bila dia infinity je.
Yes. Generator kalau kita infinity kan, sampai infinity. Sebab dalam definition of generator, we got this infinity.
Oh, okay.
Kita tak sampai k. Tapi kita cari sampai k sebab selalu kita consider finite kan. Our case we consider finite. So saya tukar kat sini infinity sebab saya try k to infinity. So maksudnya k tu kita finite, lepas tu finitely many k. So kita akan berterusan. Kalau k finite dapat banyak ni, maksudnya kalau berterusan kita buat untuk k time, infinitely many time untuk k, so kita akan dapat largest lah, kita akan dapat the largest one. Okay, good question. Okay, so yang ni saya tulis sebagai k minus 1 sebab yang ni memang kita fix to kth coordinate. So I write something. So if k is goes to infinity, then this one becomes infinity, and that means your the join of this whole partitions is equals to the epsilon. So if you got this equals to the epsilon, you mean that your psi is the generator. So the conclusion is your psi is the generator. Okay. So generally you can do for the case E. Here E is between 0 to R minus 1. Also the same, you can do the same. Ini 0, 1 je. So kalau 0 sampai R minus 1, that means this one berubah sikit je lah dalam elements ni. Okay. You can try to do the same method here unless except the numbers of fixing digit and coordinate ni adalah ada R macam ni. Psi dia ni bukan 0, 1 tapi dia sampai 0 sampai R minus 1. This one you will have also the same 0. Ni ada 4 sebab dia ada 2 kuasa 2. Yang ni akan jadi R kuasa 2 lah. Macam tu. And so on. Okay, so the question is why generator is important? Because according to our theorem of Kolmogorov-Sinai, okay, so just nak recall balik, let T be a measure preserving transformation if finite partition psi is the generator of T, then you can find the entropy of the transformation is equals to the entropy of T of the psi, where psi here is the generator. So the importance of generator is that you can find the entropy of the transformation. So kalau you know that psi is the generator, because after showing, let's say you show that this, okay, is equals to this, so that means your entropy is the same as the relative entropy of the generator. Itu conclusion dia. Boleh? Sebelum ni kita cari biasa je kan? Sebelum ni kita tak check pun psi kita ni generator ke tidak. Kita just cari relative je. Maksudnya kita cari dia punya join je kan? Using the limit. So kalau psi ni generator, straight away you can find that the entropy of this is equal to the entropy of the transformation lah. Okay, example. Example, let X be the segment of 0, 1. Consider diadik M usual Lebesgue measure. Okay, and then you have the partition psi half to 1. It has 2 elements. Okay, so in previous calculation, okay, you found already, right, your relative entropy. Your relative entropy here is what? Log 2 kan? Let's say you got this already. So kalau dah dapat yang ni log 2 and you shown that psi is the generator, thus by using Kolmogorov-Sinai theorem, then you will have the entropy of the transformation is equals to the entropy of the relative, which is equals to log 2. Is that okay? Okay. Macam kita nak kata yang generator ni macam dia punya shortcut. Macam tu lah. Tapi tak ada shortcut juga. You should know the entropy. Shortcut lah. So senang, tak payah cari supremum tu kan. So kalau you got the, you know already this to the relative. So kalau nak cari relative kan cari limit apa semua dapat log 2. Lepas tu nak cari entropy of this, you have to use the Kolmogorov-Sinai kan. So Kolmogorov-Sinai, this is equal to the supremum of the something. So kalau tak nak guna supremum, you can show that this is generator, straight away you can find that they are the same. Okay. Another in general calculations. Tak ada. Okay. So in general calculation, for Ariadic transformation. Okay. So that means you have Tx is equal to Rx in mode 1. So apa akan jadi kalau in Ariadic? So that means R greater or equal to 2 lah. So your entropy of the transformation should be log R lah. Kalau 2, diadik you got 2, triadik you will get 3, and 4-yadik you will get log 4 and so on. So R-yadik, that means you will have log R. Because you shown already that your HT, well, this is generator is log R. This one I think in the previous example. Another example is Bernoulli shift. Kalau T itu adalah Bernoulli shift, again I specify all the properties of the Bernoulli. V0, mu1 is equals to, this is P1, P1 is equals to P2, okay. And I have the psi is given by this coordinate function. First 0 and the second one is 1. Okay. And then T is Bernoulli shift. Okay. And your relative entropy is equals to minus P1 log P1 minus P2 log P2. This one we have found in Tuesday class. Oops, okay. And in Bernoulli shift also we already show that your psi is generator, right? Psi is the generator. So because of that, we use the information, and by the Kolmogorov C9 theorem, I have the entropy of the Bernoulli shift or entropy of the transformation T is equals to minus P1 log P1 minus P2 log P2. Okay.
Okay.
Boleh. Okay, let's say for particular case, for Bernoulli shift juga, for particular case, if you have P1 equals to P2 equals to 1 over 2, then your entropy of T or the entropy of the Bernoulli is equals to log 2. So kalau you have the measure, they are symmetric untuk Bernoulli shift particularly, sebab Bernoulli shift can be 1, 2 over 3, satu lagi 1 over 3, it can be as long as they are, the summation is 1. So kalau both of them are the same, or we call it as uniform, so you will have log 2. This one, okay. This one is particular. So another remark, isomorphic transformation has the same entropy. Previous in our class in lecture number 8, I think we have discussed about isomorphism. So if they are isomorphic between two transformations, so we say that they are the copy of each other. So the property that transformation A has, transformation B also got the same property. So if you know already Bernoulli dengan diadik isomorphic, so you can say if Bernoulli is entropy dia adalah log 2, so that means your diadik also log 2, the same, they have the same entropy. Is that okay?
Yes.
Alright. Okay, so generalization from our lesson today. Generalization. If E runs from 0, 1, 2 until R minus 1, and you have the measure of each of these elements until V R minus 1 equals to R, PR. Then you have the entropy of the transformation T must be equal to the minus of sum I of 1 until R, Pi log Pi. Okay. Kalau this your T ni, since E is runs from 0 until 1, 0 dengan 1 je, ada 2 elements. So actually in general form you can write your HT here as minus psi, minus sum of I from 0 to 1 Pi log Pi. Ataupun 1, sorry. Tak ada 0 sampai 1. 1 to 2. So kalau I to 1, so you have P1 log P1. So until 2, so that means until P2 log P2. So you got this. This one is the entropy for this lah. So either you can write in this form or you can write in this form. Doesn't matter. Okay. So in general, kalau E ni ada R elements here, R elements. So that means your entropy of the T of the transformation is until 1 until R lah. So you will have minus P1 log P1 minus P2 log P2 until minus PR log PR, your HT. Okay. So if tambah sikit kat bawah. If macam mana nak tulis ni? Nak kecilkan sikit. Okay, boleh. So if dia punya measure is the same, equals to P (1 over R). So kalau they are uniform, so what do you have here? So according to our example here, kalau they are uniform, you have log of that lah, log of how many elements in the E. So that means if this is uniform, you will have the entropy of T is log R. Okay. Any questions until this part? Ni faham? Boleh?
Boleh.
Okay, good. So let me recall what we have learned this for today's class. So in today's class, I recall about the definition of Kolmogorov-Sinai theorem. And in Kolmogorov-Sinai theorem, we should have at least two properties. So first, you should have the finite entropy, finite partition with the definition of entropy. And if you have the condition that they are less than or equal to eta, then you will have the entropy of psi less than or equal to the entropy of eta. And we also consider the relative entropy. So relative entropy is by finding the limit of the join of the pre-images. So the limit is exists. Either you can have finite or infinite. So, and now the Kolmogorov-Sinai theorem is said that the entropy of T is equal to the supremum of the relative entropy. So there are also ways to find the entropy of the transformation T by using the generator. So generator, so this is so generator is if you got the union of the join of the pre-images of the partition infinitely many times is equal to the largest partition. So if they are equal, that means we can say that our psi here is the generator. So if psi is the generator, then we can use the Kolmogorov-Sinai theorem to find the entropy of the transformation. So this is the examples that we considered in triadic, in diadic, in ariadic, and also in Bernoulli. Okay, so in Bernoulli, we also find that all the psi is generator. So according to the theorem Kolmogorov-Sinai, if psi is the generator, then you can find the entropy of the transformation, which means that they are the same with the entropy of the relative. Okay, and we also consider the example of the diadic, where here we know after taking the limit of blah 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 blah, we have the relative entropy is log 2, and to find the entropy of T, so we know that psi is the generator. In that form, we can say that our entropy here of the transformation is equals to the relative entropy. We also consider another example of Bernoulli shift. So in Bernoulli shift, we have two conditions. So if our E is in between 0 to 1 elements or 2 elements, so your entropy is this, which is equal to the value of the relative entropy. So if we have the measure is equal, if the measure is the same, then you will have this entropy is equal to only log 2. For the important remark, isomorphic transformation has the same entropy. So if the first transformation is equal to log 2, that means the second transformation also must be log 2 entropy. And for the generalization of our example for Bernoulli, so if you have the measure of the Bernoulli and E has R elements, so if they have different measures, so your entropy must be in this form, entropy of the transformation. So if the measure are uniform, or we can say as the same, we can have that the entropy is equals to log R, log of the number of the elements. Okay, that's all. Any questions before we end our class? Tak ada, okay. Alright, so if no questions, then I just want to let you know that we have only another one lecture, lecture 13, next week. So inshallah we will cover that, lecture 13. And next 2 weeks, last week, I would like to do a quiz. So this is your first and your last quiz in week 14, which is the last week lah. Bila? Let me see. So when do you want to do it? On Thursday or on Tuesday? So in week May, June. So June, this is the week 13, so week 14 here. Between 8 or cannot. 8 lah. Can we do 8? 8 June.
Hari apa tu doktor?
8 Jun hari Selasa.
Okey juga.
Boleh?
Tengok
8
semua.
Jun hari Selasa. Ya?
Tak apa.
So we cover from what I have start lah. From isomorphism until next week punya kelas. Is that okay?
Okay.
Maybe this one is a practice on how to find entropy apa semua lah, semua benda tu. Maybe this is a good practice for preparation of your final exam. Boleh lah, kan? So on the second class on the week 14 tu, kalau kita tak ada apa-apa masalah, we can do revision. Okay, revision from the first lecture. Okay. Okay, so thank you class. If there is no more questions, then I end this class with Assalamualaikum warahmatullahi taala wabarakatuh. So thank you for your attention and also for your patience. I see you next week insyaAllah. Thank you class.
Thank you, Doctor.
Okay. Welcome.
Thank you, Doktor.
You're welcome.